What?
All right, hello, Jace, and whoever's watching this. This is 4-1. We're starting chapter 4. You guys got to be quiet. You guys got to be quiet. We are on example 1. Let's start real quick, and let's write some stuff over here off to the side. So look at the bottom right corner of the paper. I want you to write some stuff down. Bottom right corner of the paper. Does everybody see where we're at? 4-1, bottom right corner. Perfect. Here's what I want you to write. Let's talk about linear functions, and let's talk about quadratic functions. Put them exactly like this at the bottom right corner of your page, because we're going to compare a linear function. Parent function is y equals x, right? Quadratic function, y equals x squared. What does a linear function look like when you graph it? A line. What's a quadratic function look like? A parabola. We just spent the entire chapter, last chapter, talking about just these guys. That's it. Okay? Now, from here, we're going more, right? We're going to talk about cubic functions. So put him right below linear. Cubic function is y equals x to the third power. Okay? We're going to talk about what he looks like. Then we're going to talk about quartic functions. Q-U-A-R-T-I-C. He is y equals x to the fourth power. We're going to talk about what he looks like. Okay? Then we're going to go quintic. Y equals x to the fifth power. Okay?
Whoa. Can you spread that out?
I'm not going to go x to the sixth power. We'll just go quintic. Okay?
After quintic.
I don't know what it's called. X to the sixth. He doesn't have a special name. Something like that. Okay? We're going to fill out what these look like, all right? What the parent functions look like. So you should know at this point. Are you listening? You should know at this point what a linear function looks like. He is a line. You should know that a quadratic function looks like a parabola at this point, yes? Okay? Now, a cubic function. Get this stuck into your brain now, too. The parent function, x cubed. He is
It's an N or a W.
like one of those. Okay? X to the third power. He actually, the way that I think about him is, he is like a parabola that's been flipped down.
Or cut.
You see that? Or cut in half and like flipped down, right? That's what my x to the third power function looks like. Okay? If we go over to here to quartic, do you know what he looks like?
It's a U, isn't it?
He is a
Like a W.
W. A quartic function looks like a W. Okay? That's what he is. All right? What about a quintic function?
A W, but it's like the one's down.
2 hump to W. I knew it.
He looks like that.
A W.
Okay? All right, are we ready to compare?
Like an M, but with a
This is all going to make sense. Carson, are you with us?
So what?
All right, are you writing this down?
He's not even
Okay, off to the right side at the bottom, here it is. Here is your summary of all this stuff. We just wrote down these parent functions, right? Okay, get it into your brain that y equals x to the third power looks like this. X to the fourth power, x to the fifth power. Ready?
Yeah.
X to the first power, x to the third power, x to the fifth power. The left column is all
Infinity.
odds. There you go. 1, 3, 5. These are all odd exponents, or I'm going to say odd degree, because that's what they are. Odd degree. Got it? Okay? These guys are x to the second, x to the fourth. We could go x to the sixth, x to the eighth, whatever. These are all of an even degree. Does that make sense? Okay, now there are patterns associated with this, right? What do you notice about this function and this function and this function?
They all infinity.
They all start in the bottom left and they end in the top right. True?
True.
And then they've got extra little lumpy things in the middle, right?
X
Bottom left, top right. Bottom left, top right. Bottom left, top right. Yeah?
Can it be the other way?
Okay. Now, can it go top left, bottom right?
Yes.
Yes. Okay, so let's talk about that. If you instead do a linear function, but he's facing downward, that would be like negative x, right? If I do the cubic function, he is just going to be like this instead. That would be negative x cubed. This guy here, a quintic function, if I go that direction, he's going to look like this, okay? So if it is negative, it's going to be going downhill. These guys are all positive. Those are going uphill. Does that make sense? Okay? So negative versus positive, but if it's an odd degree, it's going to go opposite directions, basically. Odd is opposite. Got it? Opposite directions. These guys are even degree. They're going the same direction. We know from parabolas that if it's a positive x squared, he's going up and up, okay? But if he's a negative x squared, he could go like this. This would be a negative x squared. He is going down and down, okay? A quartic function, he looks like, instead of like a w, what does he look like now? An m. That would be a negative x to the fourth power, okay? So we can learn a lot of things, or we know a lot of things about some functions, depending on, are they odd degree or even degree? Are they positive or are they negative? If they're positive, they're going to do one thing. If they're negative, they're going to do another thing based on odd or even degree. Make sense? Okay, if they're even degree, they're going the same direction. If they're positive, they're both up. If they're negative, they're both down. Right? Odd is opposite. They're either going this way, and that's uphill from left to right, or they're going downhill from left to right. Like this. Does that make sense? Okay? This entire table over here says all of this. All of that is incorporated into the table. Okay? So let's talk about this guy. Let's just talk about this parabola right here. He's kind of like a skinny parabola, whatever. Or like a long, he looks more like a flat tire, right? Instead of a parabola, whatever. Is he odd or is he even? Even. He is an even degree. Is he positive or is he negative? He is positive. He's going up and up, right? Okay? Let's bump over to here. Is he odd or is he even?
Odd.
He is odd. He's going opposite. Odd means opposite. Okay? Is he positive or negative? He is going uphill from left to right. He is positive. Okay? He is odd and positive. Let's go down here to the bottom left. Is he odd or even? Even. Is he positive or negative? Negative. He's going down, right? This guy, is he odd or even? Odd means opposite. Is he positive or negative? He's going down, so he's negative. Do you see how this works? We can figure out end behavior, right? Okay. All right, so let's bump to example 1. Let's do this. Describe the end behavior of this thing, negative 2x to the third power. Let's just do a little rough sketch of what he looks like. We don't have to make a table. We can just like do a rough sketch. Okay, x to the third power is cubic. He is going to go the same direction or opposite directions? Opposite. Odd means opposite. So he's going opposite directions. Is he going up or down? Down. So he's starting here and he's going opposite directions. He's going like this. That's what he looks like. Okay? Without making a table of values, I know generally what he's going to look like. Okay? Then they want us to use the leading coefficient and degree and state the domain and range. So they want us to describe the end behavior. Do you remember how to do end behavior? Yeah.
As x approaches infinity.
As x goes to infinity, what's the y doing?
Going negative.
As y goes, or excuse me, as x goes to negative infinity, what's the y doing? So put this on your graph off here to the side. And then the last thing they want is domain and they want range. Okay? Okay, so as x goes toward infinity, that's a fancy way of saying as the x's go to the right. On the right side of the graph, what's happening? He's going down, so he goes to negative infinity. Do we remember doing this a long time ago? Okay. As x goes toward negative infinity, that's saying on the left side he's going up. Okay, on the left side he's going up, so that is positive infinity. Okay. Domain, left and right, he will go all reals. It kind of looks like he's like going just straight up from here, but he will eventually go up and out as he goes, right? Okay, so all reals, range up and down. All reals. Got it? Yeah, that one's not too bad. Okay? Good, good. Let's do the check one really quick. Negative 10x to the 6th power. Okay, x to the 6th power. Is he going to go opposite directions or the same direction? Same. Is he going up or down? Negative means down. So I don't know how many humps he has, whatever. That's too many humps. There you go. He looks like that. Something, maybe. I don't know. Okay, I don't know how high the humps are, whatever. That's x to the 6th power and he's negative. Okay, so as x goes to infinity, let's fill this in. As x goes to negative infinity, on the left side, what's he doing? Negative infinity. On the right side, what's he doing? He's going negative infinity. Okay, what's the domain? Domain, he's going left and right forever. What's the range?
Y is
Less than, like, y Y is less than or equal to whatever.
Y is less than or equal to whatever the max value is. I'm just going to do that. Okay, we're not going to graph him yet. Okay, so he's going to be lower than whatever my highest hump is at, right? All the Y values are going to be lower than that. Got it?
Yep.
Good? Perfect. Perfect. Okay, we're going to skip example 2. Let's go on to example 3.
Positive. Wait.
What?
How do the humps go above?
I don't know. I just made this up. I just know he's going to have like, he's going to go down and down, and that's what he's going to look like.
Are the humps ever going to go above the x-axis?
Yeah. Yeah. Like if, let's say you have like x squared plus 4. This is a parabola that's moved up 4. Negative x squared plus 4.
Yeah,
Parabola.
There's no x.
For this one, your maximum is going to be 0. You're right, Brady. So you could say 0. We already know that, but we didn't want to. I didn't want to have you to think about it, what it was, right? So in this case, it's going to be 0. You're right. Okay. Don't ignore Brady. Don't listen to him. Okay. All right. Moving on. Example 3. Are you guys all with me? Example 3. Let's talk about degree and leading coefficient. Okay. What's a degree mean?
Like
The highest exponent. Okay, the highest power, right? The highest exponent, okay? And then the leading coefficient is the number in front
of the highest exponent.
of the highest degree. Okay, now be careful because sometimes they try to trick you. Okay, here we go. Let's do these examples. All right, so in part A, which one is the highest degree?
The 4.
The 4. Okay, so I'm going to circle the 4. So the degree is 4. What's the leading coefficient then going to be? 2. It's the number that's in front of that. Okay, now a lot of times your leading coefficient is the very, very first number out there, right? Like the absolute first number. Okay, but if they have those not written in the right order, not in descending order, like they should be, you have to be careful. All right, B, what's your degree?
3.
3, what's your leading coefficient? 7. 3 and 7. 3 and 7. What?
What's the leading coefficient?
The leading coefficient is the number in front of the x that has the highest power. Okay?
Oh, nice markers.
All right, what about C?
They're all the same.
They're all the same. This is to the second power. This is technically a second degree because I have an x and a y. This one is a second degree as well.
So it's the 8 because it's the biggest number.
Nar.
This is not a polynomial in one variable. So we don't even have to do it. Okay? I should have read the instructions. State the degree and leading coefficient. If it is not a polynomial in one variable, explain why. He's not a polynomial in one variable because of the x and the y, right? Okay? So if the fact that he has an x and a y, that makes him not work. Okay? D.
5 and 1.
His highest exponent, they have these in the right order. His highest exponent is 5. What's the leading coefficient? 1 is the number in front. Got it? These aren't so bad. Okay. Yeah. Very good. Okay, real quick, let's do the check. Let's do the check really quick. Do you guys see this thing right here? What's his degree?
3.
It would be 3 and the leading coefficient would be 11, except
X can't be on.
you cannot have an x in the denominator. So what does that mean?
Not a polynomial.
Not a polynomial. If it was a polynomial, this would be my stuff for it, right? But it's not a polynomial if the x is in the bottom. So I just want to make that clear. You cannot have an x in the denominator. That makes it not work, okay? That's not to say I can't have fractions. I could have like 1/2 x, right? But I cannot have x in the bottom. Good? All right, let's move on. Let's go to, I don't know. Example 5. Here you go. Zeros of a polynomial. What are zeros?
Where goes the x-axis?
These are x-intercepts. Okay, add that to your list. X-intercepts. Use the graph to state the number of real zeros. How many zeros does he have?
3.
1, 2, 3. They are at approximately -2,
1.
1 and 4. Yeah, I don't think it's, is it on -2 exactly? Sure, we'll call it. Yep. -2, 1, and 4. Those are my zeros. There are 3 real zeros. That's not that bad. I think you had a quiz a while back that said, state how many zeros there were. You just have to state like where